Okay, so let's start lesson 1.5, basic integration techniques. Now, depending on how long ago you had calculus or who you had for calculus, you may not really remember integrals all that much. So let's kind of go over the basic idea of what's going on. Now, I've got a little curve and a little graph to show us roughly what's going on, but I'm actually going to go to the end and insert an extra graph in. It won't let me just put it wherever I want it. I have to put it at the end. So let me just draw a little graph just to illustrate something. Okay. And let's see here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 10, 20, 30, 40, 50, 60. And I'm just going to make just like a little basic graph to kind of illustrate the difference between a function, a derivative, and an integral. Okay, so here I've got a graph, and I'm going to go ahead and label the axis. So this will be hour, and this will be number of parts. Now, one of the most common statements that people make when it comes to calculus is one, they're not really for sure what the parts do. It's not that finding a derivative is hard or finding an integral is extremely hard. They can be, but for the most part, they're not. It's that people really don't know what they're actually doing it for. And so when you come into a real world situation or into a practical situation in a science class, it never occurs to you that you could take the derivative because you don't really understand what it's giving you. And you don't know that you could just use an integral to simply solve the situation you have because you don't really understand what the integral gives you. Okay. It's kind of like not understanding that you could just rent a car or take a bus or take a plane to get from one place to another because you don't understand what airplane travels like, or you don't understand what a bus travels like, or vehicle travel. You just don't understand. So you end up just walking everywhere and you eventually get to where you want to go, but it takes forever. I'm reminded of a book I think I have in the office that I picked up when I was in college. And it was some textbook, it was some small book, math book I picked up in the bookstore. It was on clearance for like $3, and it was about physics and it had relativity on it. And I was like, I'm going to pick this up. I'm a nerd. I need to pick this up. And so I picked it up and I started reading through it. And it was trying to do physics with algebra, not calculus. And algebra based physics takes forever. It's like trying to get from one place to another by walking. It takes pages to work simple problems because you're trying to do it without calculus. And then you turn around and work that same problem with calculus and it's 3 steps, you're done. Or with vectors and it's 3 or 4 steps, you're done. So that's the main kind of focus of today's lesson, is to remind you over and over again what the integral is actually telling us and how to find it. Now, right here I have a graph of parts per hour, okay? So the first thing I want to tell you guys, or just remind you guys, is what the function tells us. Okay. The function and let's just call the function f of x, but we could call it whatever we wanted, p of t, it doesn't really matter. The function tells us how many parts we made for a given value or a given hour. I'm sorry. Boom. It doesn't tell you how many you've made for the shift. It doesn't tell you how fast you've made them. It only tells you how many parts you made that hour. That's its job. So if you need something else, you need to use something else. So if what you need to know is how many pounds of cement you made during 3 a.m., okay, that's going to be the function. If you need to know how many bacteria cells you have in hour 8, that's going to be the function. If you need to know how many meters you've traveled during hour 5, that's going to be the function. It doesn't tell you the total amount that you've traveled, and it doesn't tell you the speed. So if you have a function for height, it will tell you the height at a given moment of time. It doesn't tell you the total height that you've climbed. It doesn't tell you the speed that you're going up or the speed that you're coming down. It only gives you the height at that specific moment of time. Okay. Now let's move on to the derivative. We talked about derivatives last time. That was lesson 1.4. Okay. The derivative and I'm just going to use f prime of x, okay, as the symbol, tells us how fast we are making parts. So the derivative is speed, called rate of change. Okay, that's what the derivative tells us. And I need to put my phone on silent. There we go. Now, if it's negative, that means you're losing. It's going down. Positive's going up. Zero staying the same. But the derivative tells us how fast. So if you need to know the speed, which is velocity, then you need to find the derivative. If you need to know the acceleration, that's the second derivative. So speed, okay? If you need to know how fast something's changing, so let's say you're a diver and you need to know how fast the pressure's changing, then that's a derivative, okay? If you need to know the pressure at a specific depth, that's the function. So the pressure at a certain depth, that's going to be the function. The speed at which the pressure is changing is the derivative, okay? Now the integral, which is the main point of Calculus 2. Calculus 1 is to introduce you to derivatives, get you comfortable with derivatives, and maybe at the end touch on integration. Calculus 2, our main job is to get you comfortable with integration. Calculus 3, we start to do derivatives and integrals in 2 and 3 dimensions. Calculus 4, which is differential equations, is to use integrals to undo derivatives. So you may remember this from Calculus 1. We'll talk about it today. But if you have a derivative, the integral, or if you want to call it the antiderivative, can work backwards from that and get you to your original function. If you have the second derivative, which is acceleration, you can work backwards to get to your original function. Okay. So the integral, its main purpose, though, not to undo derivatives, but its main purpose mathematically the integral which is, I know there's a symbol for it, but I'm just going to go ahead and write the symbol that everyone really recognizes as integration. The integral tells us the total number of parts we have made, have made from time A to time B. Most of the time in math, we do have an A and a B on that symbol. Not most of the time, but some of the time. And that just says from hour 5 to hour 8, how many parts have you made? From hour 2 to hour 6, how many parts have you made? So that is what the integral tells us. It adds up. It's a summation. It adds up what we've done. So if you've been working all day and you're like, man, what have I accomplished today? The integral will do that. Or scientifically, if you, just for sake of argument, let's say you have a table, okay, or just anything, but some big, huge chunk of something, an asteroid, whatever, and I tell you that this little bit, if I tell you how much that small little bit weighs, then you can use an integral to add up the entire amount of that object. So if I give you the dimensions of an asteroid and I tell you that the asteroid is made of copper, well, you just look up on a table how much copper weighs and you use an integral to add it up over the entire size of the object or the asteroid or whatever. And so using an integral, you can take a small chunk of something and just add it up. You may have seen the movie The Fifth Element, and if you haven't, pull it up. It's great. I think it's still on Netflix. I own it twice, but it's a really great movie. And at the beginning, I know this is spoilers, but it goes to this point. At the beginning, they have this. They have a small part of someone's DNA, just a small part, and they're able to use technology to regrow that person back to where they were. It makes no sense. And their memories, everything. It makes no sense. But they basically cloned them from one small bit of cells. And that's kind of like integration. If I give you a small piece, how can I then expand that back to the original? And that's kind of the big challenge of Calculus 4, differential equations. If I give you a small piece, get me back to the original. Okay, expand that back out, add it all up. All right, so now that we've done that, let's get back to the beginning. So mathematically, we call adding up all of those pieces the area. Okay, but really all you're doing is saying, what is the total right there? That's what we're saying. So right here, if we're just looking at this right here, that is 1 over x. I'm just going to use my calculator, which I'll show you guys how to do that. I don't have the program on this computer, so I can't really show you today, but I will get that in one of our future videos. So I'm just going to add that up from 1 to 6. And that is 1.79 parts were made from hour 1 to hour 6. If you want to look at it as parts, you could look at it as a region of space, and we're trying to figure out how many particles of carbon or hydrogen there are in that region of space. Or this could be a plot of land, and you're trying to find the acreage. So that could be almost 1.8 acres of land, or 1.8 square miles of land. So it could literally just be square footage. But or it could just be like, well, how many groundhogs are in that backyard, or how many deer are in that piece of wood? So it could just be that. So the applications are endless because you're just trying to find how much of whatever it is you're concerned about you have. And no one has nothing that they're not concerned about. Everyone's got something that they are concerned about, and they want to know how much of it they have. Could just be money. If you're a business, you could be like, well, I've got $1.79 billion that I've made from January to June, whatever it is. All right. Now, just like we mentioned, one other use, and this comes up a lot in Calculus 3, and we'll do a whole section on it here, is to find the area, not between the curve and the x-axis. That's actually still top minus bottom. So right here is the x-axis. That would just be y equals 0. And then right here is the top. So really what you're doing, every single integration function could technically be written like top minus bottom. So right here, the only thing that's changed is the x-axis is no longer the bottom of the graph. So on the previous example, it was really 1 over x minus 0, and no one ever writes minus 0 because it doesn't do anything. Here, it would be 5x minus x squared minus x. So this is what this one would look like, top minus bottom. And this would be your start, A, and this would be your stop, B. And that is how you would go about doing it. Now, I do want to show you guys how to find a start and stop. So if you look at this one right here, you can see that it looks like it starts at 0 and stops at 4, okay? Because we have a good graph and we have a good grid that shows us what the x and y axis looks like. That is not always the case, especially those of you, once you get into your engineering and your physics classes, you're an engineer. Your job is to figure stuff out. So do not expect to be given a lot of information. One of my optics classes, I walked in first day of class, well, first day of lab, and the instructor said, okay, your job is to figure this out. Just gave us something we had to find, like as light goes through a fish tank full of water and salt, how much does the light deflect by? And we're sitting here like, oh, well, there's probably a formula. No, you have to figure it out. You can use anything in this room. And if it's not in this room and you think you need it, come to me. I have a budget. We'll go to Walmart. We'll go online. We'll buy it. And you're sitting there going, whoa, I'm used to walking in and everything is set up for me. I just press some buttons, read an output, and type it in and write up my lab report. I'm used to everything being done for me. That's not an engineer. Everything's not going to be done for you. So I want to show you guys how to actually find your start and stop, because there's going to be times where you won't have that given to you. So to find a start and stop, step 1, set your equations equal to each other. So to find the start, stop, set your functions equal to each other and solve. So that's going to be 4 plus x minus x squared equals 1 minus x. Okay, now to solve something to the second power, we are going to get everything to the same side. So I'm going to move this over. And I'm going to move this over. Doesn't matter which side you move them to. You can move everything to the right-hand side if you wanted to. If I could write plus x, that would be very handy this morning. Okay, so this is going to be 3 plus 2x minus x squared equals 0. Okay, now I'm going to rearrange this and put this piece first and this piece last. So I'm just going to rearrange it and put it in what we call in math descending order. So you start with your biggest piece and go down. And so that's going to be negative 1x squared plus 2x plus 3 equals 0. Okay. Now, there is an alternative reason I wanted to work this one. You need to be able to solve something to the second power. You probably went over it in your algebra class, but that could have been a while ago. It could be years ago. It could have been high school. It could have been middle school. I don't know how fast you guys went through stuff. But I took algebra in middle school. And I took it again, like freshman year of high school, but then it was pre-cal, calculus, we were moving right along. So it could have been forever ago for you guys. You have to be able to solve stuff to the second power. I'm going to get some extra notes up on Blackboard to help you guys out, but you have to be able to do it. And that means that you need to be able, not need, have to be able to work the quadratic function. So the quadratic function, this is A, B, C. It has to be in descending order. And then the solution is negative b plus or minus b squared minus 4ac all over 2a. Okay. So I'm just going to plug my numbers in. I did get a little lazy here. This should be in parentheses. Okay. And then that's going to give me two answers. And I think one of the answers is -1 and the other one is +3. Okay. So this is going to be my start. The -1 right here is my start. And the +3 is my stop. Boom. Now that I have my start stop, I can plug everything into the function or the formula. So area is equal to the interval from -1 to 3 of the top, which is 4x x squared, 4x x squared minus 1 minus x dx. So that's the top and that's the bottom. And this is the start and this is the stop. And you type this in your calculator and you get the area is 10.6 repeating. Now, keep in mind, that could be how many parts you've made from 1 a.m. to 4 a.m. or whatever it is. It could be how many crickets you have in your backyard. Whatever it is that you're dealing with, that's how many you have. Now, if it's negative, you've lost that many. If it's positive, that's how many you've gained, you have over that time period. Okay. So that's what we are looking at. Okay. All right. Now I do want to, while we're here, say one important thing. How do I know Does the start and stop always have to be in numerical order? No. You can go backwards. Unless you're told otherwise, assume you're going forwards. So -1 to 3. But you can actually go backwards. This happens more in Calculus 3 when you're integrating on rotation. And so you're going from 15 degrees as your start and 40 degrees as your stop. You can rotate backwards. And so you do not have to have your start and stop be in numerical order. It can actually be flipped depending on the situation you have. Typically, if you flip the order of integration, it just changes your sign. So if I was to flip these, my answer would probably be -10.6 repeating. So that's basically all that's going to do. All right, so there's a couple of very important rules that you need to know when you're trying to work on an integration problem. The one that I'm going to focus on is the power rule. If you're good with the power rule, that is the majority of the integration that you will have to do. So all that is the first thing you're going to do is start with your function inside of here, and you're going to find the antiderivative. Some people say integral, some people say antiderivative. The antiderivative is just undoing the function, working backwards. So this is 6x cubed. I'm going to work backwards. So what you do is you take the exponent, the power, and you add 1 to it. Okay. Then you divide by your new exponent. Okay, so add 1 to the exponent. Divide by new exponent. And that's the power rule. Now, I should clean this up a little bit, and I'm going to down here. So now that I've done that, I'm going to reduce that. That's going to be 3 over 2 x to the 4th. Okay. Now I'm going to introduce you guys to a new symbol. You do not put this back into the whole original thing anymore. So this part right here, let me circle this. This part right here now gets converted into this, a straight vertical line. And you put x equals 2 at the bottom and x equals 5 at the top. So that gets converted into that. So it comes down, and that's get the new symbol for it. So don't let that symbol confuse you, okay? And then all I'm going to do is work this out. Top goes in first. So 3/2, 5 to the 4th, minus 3/2, 2 to the 4th. And it is always minus. That's part of the problem. So it's always a minus. And so let's type this in and see what I get. And for some reason I thought I was going to get a different answer. I get 913.5. Okay. So while you guys get up to here, I'm just going to use my calculator to double check myself, just to make sure. I don't remember having too many decimals on this set of examples. But no, it backs it up. Okay, so that one does work out to be in a decimal. Boom. So that's how much we've gained. Any questions about this? We're going to do a few more examples of this. Okay. So let's do this one right here. So step 1, use power rule to find antiderivative. Okay. Now, if you've got addition, there's a nice handy rule that you can use. if you have addition, you can treat this as two separate problems. So that's going to be 3x to the 2 plus 1. Now this is already to the first power, so when it comes down, it's going to be 1x to the 1 plus 2. Okay? And then it comes down again, and that's going to be 3x to the third divided by my new exponent. Oh, that should not be a plus 2, that should be a plus 1. Boom. And so now that I have this, I can move on to step 2. Complete the integration. Now, if you do not have a start and stop, you would stop right up here and you would just tack a plus C on that you may remember from Calculus 1, and that would be it. That'd be all you could do. So, but for us, we're going to keep coming down, and so that's going to be x cubed plus 1/2 x squared. And I'm going to use my little integration symbol there now, and that's -2 to 10. Boom. Type that in my calculator. I think my calculator just broke. Okay. There we go. Pop the battery out. Pop it back in. All right, that's going to work now. -2 to 10. 1056. So this gives me 1056. Cool. All right. Any questions about that one? Any questions at all? All right. So I'm going to do the same thing over here. So let me, instead of having to rewrite all of this again, just going to bring that over here. All right. Save myself a little bit of time. Okay. Now, one thing I wanted to show you guys, again, we've already talked about this one, that's to the first power. If you have a letter that's all by itself, that is actually x to the 0. The exponent just tells you how many copies of something you have, so that's saying you have no copies of x. Really, I need it there so that I can add 1 to its exponent. So this is going to come down, and that's going to be 8x to the 1 plus 1 minus, this is going to come down, and that's going to be 7x to the 0 plus 1. This will give me 8x squared over 2 minus 7x to the first over 1. And then I'm ready to go. Comes down to here. This gives me 4x squared minus 7x. And I am going from 0 to 18. Okay. So that's going to be 18 squared minus 7, 18 minus 4 times 0 squared minus 7 times 0. And this is going to end up being 1170. All right. Any questions about that one? Any questions at all? All right. Okay. Now, right here, I've got some integration formulas for you that you may remember. And I don't have a lot of them on here. I need to expand this. Or maybe they just didn't show up when I converted this into a PDF. That could be the case. So I do want to add a couple more on here for some reason that are not on here. One of them is cosine of AX, and that converts into 1 over A sine AX. Another one is sine AX, converts over into negative 1 over A cosine AX. And then there's a couple more. If all you have is a number, the integral of that number is going to be that number times x. Okay? And if all you have is a single, actually, stop right there. Yeah, that's a good one to have down. Okay, so let's look at this. Now, there's one rule about this that I do want to go over because we really need this to match. What I have is I have the integral of cosine of AX dx is equal to 1 over A sine AX. That's what my formula says on the left-hand side. And it's almost a perfect match. Boom. A is the 4. Now the problem is this 7. There's nothing down here for it. And that's a problem. When it comes to using integral tables, it has to be an exact match. So there's a rule that we're going to use a lot. And that is if you have multiplication, just a number, no 7x's, just 7. If you've just got a number, then you can yank it out front. And so this will turn into 7 times the integral of cosine 4x dx. Okay. Now the a's match up, and there's nothing out here. I should do that in green. Let's go back 2 steps. Should have really been a little more careful right there. All right, so now the fronts match up, and now this is going to give me 7 times 1/4 sine 4x. Okay, so now that I've found my antiderivative, this is all step 1. Step 2, now I can bring that down as 7 over 4 sine 4x from x equals 0 to x equals pi over 2. Now, when you're doing trig in this section, you need to be in radians. If you see pi anywhere, you're in radians. If you see a degree symbol, you're in degrees. Okay, so you do want to keep that in mind. And now I'm just going to plug this stuff in, and that's 7 over 4 sine of 2 pi minus 7 over 4 sine of 0. Part of me wants to think this is going to work out to be 0. Let's make sure I'm in radians, which I am not, so that was good. And that's going to be 7, 4, It's going to take a while because it's trig. All right, let everybody get up to here. Okay, so we are going from 0 to pi divided by 2. And yes, it gives me negative 2.112 e to the negative 13, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 1, 2. Okay, or 0. So that works out to be 0. Now, the reason why I simplified that to 0 is because sometimes, and we'll talk about this later on in the semester, your calculators have trouble with trig, and they don't give you the exact answer, especially when it comes out to be 0. You end up with silly stuff like this. Newer calculators are better, but especially the older calculators, they do not handle that well. And the older the calculator, the worse it tends to handle it. And it's because of how they're programmed to handle trig. Okay, so as a math person, you need to understand that and be prepared for that. Sine of 2 pi is 0. Sine of 0 is 0. So that's where you need to be a little bit more knowledgeable than the calculator so that you can interpret that. All right, so here I'm going to remind you and kind of show you about Calculus 4. So one of the uses, especially in science, this is mainly how you're going to use integrals in science. In science, the vast majority of integration is simply to undo a derivative. So right here, I have a derivative. Now remember from Calculus 1, you can write a derivative as dy over dx, and this is called the differential. That's why Calculus 4 is called differential equations. This is a differential equation. Now, what you learned in Calc 1, you learned, or you may have learned, if you're given y equals 4x plus 9, you were mainly told that y is equal to the integral of y prime. So y is equal to the integral of 4x plus 9. You were told that the integral could undo the derivative, which is true. But there was a lot of steps that were skipped. How do you jump from here to here? That was never really explained. I'm going to explain it to you because you need to understand this for your science classes. And it helps you in Calc 4, don't get me wrong. But it really will help you in your science classes kind of understand what's going on, because symbols like this, dy over dx, that's fairly common. These types of symbols are fairly common in your science classes. It's not going to be a y and an x. It may be dp over dt or dv over dt. It's usually dt on the bottom, but it doesn't matter. It's all solved the same way. So what I'm going to do is I'm going to take my dy over dx equals 4x plus 9. Okay, and I'm going to move this dx over, and that's going to give me dy equals 4x plus 9 dx. Okay, now everything in math can be undone except division by 0, and we've tried with limits, and we're getting better, but still. Everything in math can be undone. So how do you undo a dy? How do you undo a dx? How do you undo a dp or a dz or a d rho or a d theta or a d phi or a d smiley face, whatever you have? That's the integration sign. So the integral undoes the d. Boom. Now, right here in the middle, if you have integration with nothing there, that is not a 0. That is a 1. And then just like I told you guys on the previous page, if you have the integral of just a number, it's going to be that number times the letter. And we know that that's just a y. So that is where that rule came from in Calculus 1. Now, why do I show you this? Because over here, right here, that's not always a 1. Sometimes that's a 7. Sometimes it's an 8. Sometimes it's an entire equation. So if that was an 8 sitting right there instead of a 1, you would have to move that over to the other side to finish out the problem. And that is what we start to do in Calculus 4. We start to do that. Okay. And then we can just finish this up. Y is equal to 2x squared plus 9x plus c. Boom. If you do not have a start-stop, you have to use your plus c. So that is one of the most important uses of an integral, is to undo speed. Because speed is something, or it's not just speed, it's also the differential and the rate of change. It's more than just how fast you're going. It's hard to explain everything that little fraction up here encompasses. The differential basically is just a ratio comparing two items. And it's so versatile that it's hard to encompass in just mere words everything that affects. And that right there is the biggie. Being able to look at that fraction and go, I can undo that. I can deal with that, and I can solve it for what I need to solve it for. That is big. Okay, so let's move on and talk about that a little bit. Now, later on, we'll go over this a little bit more, but you have the acceleration of an object is 18 feet per second squared. Find the velocity of the object. Now, we did not write that over there, but acceleration is actually dv over dt. That is what acceleration is. It's exactly what it is. It's that differential. So what we really have is dv over dt is equal to 18 feet per second. That's really what we have. So let's solve that. dv over dt is equal to 18. So if I move that over, that's going to be the integral of dv is equal to the integral of 18 dt. Boom. Now I'm not going to go through all the in-between steps. I'm just going to go ahead and write the v that I know I have over here is equal to 18t plus c. Boom. Boom. So there's my velocity function. Done. Now, I need to use my initial conditions to find that plus c. So I know, actually, they want me to I'll take that back. They actually gave me the start and stop. I jumped ahead of myself. So I apologize for that. They actually told me from 7 to 18. So v is equal to the integral of 7 to 18. I'm sorry, not 18, 28. I am just having a horrible time with this problem. That's at 28 right there. And so v is equal to the integral from 7 to 28, 18 dt. Type this in my calculator. And 18 window, that's going to be 230. All right, 7 to 28. All right, so that's going to be 378. Boom. So the speed of that object has went up 378 meters per second, or feet per second. I'm sorry, we're in feet. Okay, I jumped ahead to this one. All right, so this one we do not know the start and stop. So this is the one I jumped ahead to. All right, so part one, acceleration is equal to dv over dt. So we have dv over dt is equal to 18. Actually, we're in x's, so let me switch this to an x. dv over dx, 18x plus 10. And that's all that is. If you're in x's, you've got a dx. If you're in t's, it's a dt. Okay, no big deal. The actual math does not change. So I'm just going to move this over. So that's going to be the integral of dv equals the integral of 18x plus 10 dx. So this is going to be v equals 9x squared plus 10x plus c. Boom. So there's my velocity. Now I do need to find that plus c. So we know that for x equals 5, v equals 19. So all we have to do is plug the 19 in for v into 5 in for x. So this will give us 19 equals 9, 5 squared plus 10 times 5 plus c. So 19 equals, clear this out, 9 times 25 plus 50, 275. Move that over. Negative 256 equals my c. So my final equation is v equals 9x squared plus 10x minus 256. Boom. So there's the velocity. Now the next thing they want me to find is they want me to find the position. And so that's going to be another differential equation. So position, which is usually the letter R. Do I give that position? It's usually the letter R, so let's go R. R, well, V is equal to dr over dx. So we have dr over dx is equal to 9x squared plus 10x minus 256. Boom. Then I'm just going to move the dx over again. So that's going to be the integral of dr is equal to the integral of 9x squared plus 10x minus 256 dx. So that's going to give me r equals 3x cubed plus 5x squared minus 256x plus c. Okay, so there's my position. And then in step 4, I've not used red yet. Let's go with red. We know the initial just means x equals 0. We know that at x equals 0, initial means 0. At x equals 0, r is equal to 15. Okay, so all we're going to do is plug that in, plug that in, plug that in, plug that in. And so we get 15 is equal to 3 0 cubed plus 5 0 squared minus 256 0 plus c. So 15 is equal to a bunch of zeros, which is equal to c. So our final equation for position, r, is equal to 3x cubed plus 5x squared minus 256x plus 15. There we go. Any questions about that one? Any questions at all? Now, these are long problems. Are they hard problems? No, they're just time consuming. I mean, it's been going an hour just to do these problems. Just takes time, that's all. All right, so I'm going to end it there and get ready to come to work because this is early in the morning and I'm doing this before driving into work. So I'm going to get ready to come to work. I'll see you guys in an hour because it's an hour and a half, something like that. So I'll see you guys soon and we'll do this in class together today. And then you guys can get started on the homework, which is due Sunday. I shouldn't say that because if I'm using this for the spring, it may not be Sunday, but whenever the homework is due. All right, so let's stop the recording.